Okay, so this is group number 4, Team B's presentation on question 9. So in question 9, it's a two-part question from chapter 6 being problems 84 and 85. The first part goes, if the intensity of the load W equals 15 kilonewtons per meter, determine the absolute maximum tensile and compressive stress in the beam. And then the second part is, if the allowable bending stress is 150 megapascals, determine the maximum intensity of W of the uniform distributed load. We have our diagram showing our weight W, our two connections. This A connection would have an X and a Y force because it's a pin connection. Since B is on a roller, we're only going to have things in the Y direction. We only have a force going vertically, so we're only going to have a force in the Y direction. This figure down here will demonstrate our cross-sectional area of the beam, gives us our measurements that'll be useful later for our moment of inertia equations. So to start out, just drew out what we had and what we were given. We have our weight, our points, we have the distance between, we have the weight given, the allowable stress given. For the first part, set up a free bar diagram or free body diagram showing that we have a 90 kilonewton load at the center point because we have 15 kilonewtons per meter across 6 meters. And then we'll have reactionary forces at the two foundational locations being split in half. To go further, we set up an internal shear as a function of X. So we split it leading up into that first 3 meter point. We're going to have our weight distributed as X approaches 3. We have our 45 kilonewton force, and then we're going to have some sort of internal shear and some internal moment. It's easy to find the internal shear because you could just do the sum of forces in the Y direction. We'll have our 45 kilonewtons reaction going up. We have a negative 15 times X, which would be whatever distance here. That's our weight force going down. And then we're going to have some sort of shear force going down as well. And using that, we can determine that the shear force within this part of the member is going to be 45 minus 15x. Later on, you can use that in understanding that the maximum moment occurs when that shear force is equal to 0. So then we can take that previous equation, set it equal to 0 to figure out that x distance is 3. Now we are going to set up our moment equation, which would have whatever the maximum moment would be. In addition, you're going to have the 15 kilonewtons per meter times the 3 meters times 1.5, because it would be 15 kilonewtons per meter distributed across the 3 meters, and then the distance where it's actually going to be acting upon this member is going to be 1.5 meters in. This 45 kilonewtons is going to be 3 meters away from our origin. And then we could use that to determine that the maximum moment would be 67.5 kilonewton meters. Next, we're going to go and do our area moment of inertia equation for that triangular cross section that we have up here. Doing the equation that we have in the, I believe it's the appendix of the textbook, you know that it's 1 divided by 36 times your base times your height to the third. Our base would be 0.15 because it's 150 millimeters, which would be 0.15 meters. Same thing goes for the 300 millimeters. And then that's going to give us 0.1125 times 10 to the negative third, and that would be meters to the fourth. Now going for the max bending stress, we're going to use the equations we had in class to determine that maximum stress. For the top end, we're going to have our moment times that distance to the top from the neutral axis divided by our area moment of inertia equation. So plugging all of those in, we'll get 120 megapascals, which would be a compressive force. It would be a compressive force because that weight acting on the beam is going to cause it to sag. And the sagging in the beam would show that above the neutral axis, you're going to have forces going towards the center. And then on the bottom, you're going to have forces going out. The bottom of the beam is getting stretched while the top of the beam is being shrunk down and compressed. The maximum bending stress on the bottom of the beam would be the same thing as we did for the top, except we're going to be doing the distance from the neutral axis to the bottom of the beam. And taking that, you'll get 60 megapascals, and that would be in tension. Similar to number 1, which was finding that maximum bending stress. For number 2, we have everything except for that weight. And instead of being given the weight that's distributed on the beam, we now have the max allowable shear bending stress. So we set everything up similar to how we did previously, except for when we get to that moment equation. Inside of the moment equation, we will solve for the maximum moment in terms of W because we no longer have that W value. And then when we get to doing the allowable bending stress, we now have the allowable bending stress. We don't have that W, which is a part of that moment equation, but we do have the C and we do have the I. So then we can solve for the W, which would give us 18.75 kilonewtons per meter.